All right, so now we're going to use Biot Savart law in the infinitesimal expression of it to derive a bunch of expressions for magnetic fields due to current carrying wires. So here's one, and this is taken out of your worksheet. It's not solved in your worksheet, but this is given in your worksheet. So derive an expression for magnetic field B at this location here due to a current that flows through a straight wire some distance some distance d away. And I think a similar, from what I'm reading here, a similar problem is solved in your textbook. You need to know how to derive this thing, and you need to know how to derive. I think there are three problems. Anyways, this is one of them. So let's do that. The end result should look like this. The magnetic field at this point here should have this expression, and then if L is very, very big, that is, if L is much bigger than D, if the length of the wire that we're considering is much bigger than the distance D, then the magnetic field should simplify to this expression. All right, so first let's derive this, and then once we have that, and from here end up all the way down here. So let's restate the Biot Savart's law. I'm going to state it in a magnitude form, so not in a vector form, but in this way: dB equals mu naught over 4 pi times I times dl, some small segment of the wire, times sine of the angle theta. And remember that this angle theta is the angle between, well, I have it in the picture, it's the angle between dl and r, where r always points from dl to the point of interest, and this is divided by r squared. Was it squared? Yeah, by r squared. Okay, so we have this. The current I is considered to be constant, so this is a constant. So keep that in mind. Well, let's go ahead and find an expression for r in the first place. So what I can do is, by looking at the picture here, you should see that r is equal to x squared plus d squared. So I'm just going to write that r equals x squared plus d squared. And to be more precise, r squared, right? It's r squared equals x squared plus d squared. So I can replace what's on the bottom here. dl, the way I set it up, it's just going to be the same thing as dx. Since I have dl pointing in the same direction as dx here, as x, I could put my origin O at this location, and then x runs in this direction, and so and I'm going to, well, anyways, dx becomes dl. And then the next thing, well, okay, so let's write what we have. Some things change. So we have dB equals mu naught over 4 pi times I times dx instead of dl times the sine of the angle theta, and this divided by r squared, which is x squared plus d squared. Now sine theta. So here's my angle theta. It's the angle between dl and r. But sine of angle theta is the same thing as the sine of 180 minus theta. And if this is theta, then this angle here is 180 minus theta. Now I need an expression for sine theta. Well, that would be the same thing as an expression for sine of 180 minus theta, and sine of 180 minus theta is simply d over r. I'm looking at this triangle here, and so this becomes d over r. So I can take this here expression for dB, and I can rewrite this I times dx times, instead of sine, I'm going to have d over r, and then divided by x squared plus d squared. So let's set there. But d, rather not d, in one d. What I want is r. R is x squared plus d squared, and that would be the square root of it. So I can rewrite this equation one more time. db equals mu naught over 4 pi times I times, well, d is a constant. D is a constant. I'm interested in the magnetic field at a very specific location, d away from the wire, so d is a constant. So let me put d here. Times dx over, and then r, is this, goes in the bottom. What I end up with is x squared plus d squared to 3/2. All right, and that will do, because now I'm ready to integrate. And the reason being is that this is a constant, this is a constant, this is a constant. I just have dx and x in the bottom, so that's an easy integration. So what I'll have is the magnetic field. Let me write this here. The magnetic field at my point of interest, which is here, is going to be the integral of mu naught over 4 pi times I times d times dx over x squared plus d squared. This is the 3/2. All right, now, so I'm integrating from 0 to some final b. But here what I'm integrating from to is dx. Well, I start at, so I want to include the entire length of the wire here. And so I'm going to start at some 0, and I'm going to integrate all the way to L, so that I include the full length of the wire. Right? The wire starts at no length and then it runs to some length L. So my x should vary from 0 to L, and let's see what we get out of that. So maybe this is easy enough to do. You can use any software you wish to do, or something out there on a website, on some website somewhere. The end result is the following. I'm actually just going to copy the answer here, because this is going to be the end result. So what we'll have here is mu naught over 2 pi, copy and write, over 2 pi times I times L, the length of the wire, divided by d times L squared plus d squared square root of that. So this is it. This is the expression for the magnetic field at this location due to the wire of length L. Now, if, I think I'm going to leave this for you as an exercise, but if length L is much bigger than D, in other words, if I have a wire and the wire is very long, and I'm interested in the magnetic field very close to the wire, so somewhere here maybe. This length here is, length of the wire is long, and I want to find the magnetic field very close to the wire, so there's, my D is very small. Ooh, that's going to be tough to draw, but there's D there, since D is a lot smaller than L. If that's the case, then you can play around with this equation a little, and you can show that the magnetic field is going to be mu naught times I over 2 pi times d. Now you should be able to figure this out on your own, but I think I'm gonna show you at least a few steps. So let's take this equation here and let's play around with it a little. What we'll have is mu naught over 2 pi times I over d, and times L over. I'm going to rearrange this so that I have, let's see, I want to pull something out of it. D is much smaller than L, so I guess what I'll pull out is L. So if I take L out, I'm going to have L and then the square root of 1 plus D squared over L squared. Right? If I distribute this L, if I put this L back under the square root, then I'm going to end up with the same expression that I have up there. So then what happens is this nicely cancels out, and what I have now is just this expression. And from here, if d is much less than L, then d over L is roughly 0. And that implies that this equation then, equation here, then becomes mu naught over 2 pi times I over d times L1. In other words, I get the expression I wanted. This is just mu naught over 2 pi times I over d, which is what I was after. All right, so now you have this one derivation, finding the magnetic field close to a wire that carries a current. As long as the wire is straight, this would be the equation you would use. But if you are in fact interested in the magnetic field of a wire at a location that is close enough to the wire, yeah, I guess, then you would use this equation here. And this will come back later on. In a few more videos, you're going to see this equation one more time. Okay, this will do.